So we're going to be looking at the 5 ingredients that we believe are really key to forming these world-class gold systems that we see in Victoria. It should have been really it's specifically about the Bendigo zone, so not about some of the other deposits we do find across Victoria. So let's just straight in. If we just hop onto Google and just search orogenic gold, we get over 500,000 hits. If we put in orogenic gold in Victoria, we lower those amount of returns, obviously, but we get nearly 150,000 results. And kudos to our marketing team. Our website is the #1 hit when you Google that. In terms of academic research that's actually been completed on the Victorian gold systems, nearly 1 in 5 peer-reviewed papers contains mention or results about orogenic gold systems in Victoria. So there's been a large amount of research completed on these deposits. And as Ross said, we're approaching 2% of the world's gold from a very small fraction of its continental surface area. So we need to be in the right place at the right time, and there's multiple reasons why a gold system doesn't form, probably more reasons why it doesn't form rather than it forms. So we need to look for a series of geological events, processes and conditions that coincide in both space and time that generate gold mineralisation. There's multiple stages at which that can break down, as the diagram on the left shows. But across central Victoria, we've got evidence that during at least those 3 periods, those orogenies that Ross was talking to, gold was mobile and became concentrated in economic quantities. So a good place to start is at the end. So these are the 5 key ingredients that are in the Victorian pantry. So we're looking at the tectonic triggers, those 3 orogenic events between 445 and 380 MA, which were all related to inversion in a back arc position. And that allowed a series of seismic events to generate crustal scale fluid flow. Metal and fluid sources. Again, we've got 2 good candidates that academics argue back and forth about which is more important, those turbidites, those carbonaceous material and those turbidites, or those metabasalts. But hey, who cares? And maybe the fact that we actually do need both of them to generate these world-class gold deposits. The fluid source, we'll get to that. There's only a single fluid source. The pathway architecture, we see from that GSV-led seismic data that it's a V-shaped geometry with first-order crustal scale faults. So in the west, they're dipping east, and in the east, they're dipping west. And the shallow portions of those can easily become reactivated. But what is key are those inflection points where fluids escape because they can no longer go up those steeply dipping structures where they become steep and they're being held shut. So they escape along second-order structures. And then if we think about structural and physicochemical traps, we'll see that there's flat portions on the deposit scale that are important dilation sites, so specifically where those meet anticlinal structures that dilate a lot during compression or transpression. And there's numerous physicochemical parameters that change in these systems that allow us to precipitate gold. And as well, those processes don't necessarily need to be very effective, and that's why we get gold precipitated out over a large vertical section of the crust. And then we'll briefly touch on the dispersion and preservation history of these deposits, but what is key is throughout the 3 orogenic events, essentially gold's been forming, and then that orogenic events have created increased denudation rates. So progressively during those 3 events, the gold systems have actually been brought up closer to the surface, so they've been partially unroofed. And then essentially between the Devonian and the Cretaceous, there was a period of tectonic quiescence when the Lachlan fold belt had actually been cratonized. Before we get into those ingredients, I just wanted to spend a bit of time discussing geochron data. There's a lot of available geochron data for the Victorian goldfields. It's not all plotted here. What I've done is I've picked and chosen specific dates that are pretty high quality dates, which give us more confidence that we're actually dating some real geological event. One issue with a lot of the data is a lot of it's argon-argon. which is susceptible to various issues, including resetting and issues to do with grain size. But the takeaway message is that in the Benambran, we've got evidence of mineralisation from Ballarat East, Ballarat West, Bendigo, and in between those two Bs, between Ballarat and Bendigo. So that was around 445. Then during the Bindian, we've got evidence of more gold coming in at Ballarat and between Bendigo and Ballarat. And then in the Tabarabaran, so 380 to 370, we've got more gold coming in. There's a lot of data in that Tabarabaran space, and a lot of that might be related to that's coeval with intrusion of a lot of granites in Victoria. Another thing is if we start tearing apart the paragenesis, and some studies were better at documenting the paragenesis of these samples that were dated, better than others. If we look at those ones that are associated with the Benambran orogeny, we kind of start to see a consistent pattern of those that are related to directly with arsenopyrite. Then if we look at the ones associated with the Bindian orogeny, there seems to be a quartz carbonate association. And then the Tabaraba orogeny, there seems to be a quartz stylolytic and antimony association. And that's significant for when we look at deposits like Fosterville, and we see in the upper right-hand corner here, we've got gold-hosted or arsenopyrite-hosted gold mineralisation in that example. And that is obviously cross-cut in time, and we're not sure about the time gap between those two styles of mineralisation to the high-grade visible gold that we see at depth. So that's something significant to keep in mind. And that hydrothermal history is related in this example. So this is a pyrite laser ablation map where we see a low gold but high arsenic tenor as kind of associated with a moderate gold event. But then we see on the edge in the light blue, we see pyrite with really high gold and no arsenic. So that pattern that we're seeing, at least paragenetically with cross-cutting relationships, we're starting to see at smaller scale in individual grains in the deposits. Won't dwell on this too long because Ross did a pretty comprehensive coverage of this, but the tectonic triggers, so at the large scale, they're the three back arc inversion events followed by transient extension, and that's based on far-field subduction zone advancement and retreat, and that generated up to 70% shortening in the Bendigo zone. The tectonic events were largely focused in that V-shaped geometry in between the Delamerian orogeny to the west and the Selwyn block to the east. And a lot of the gold production from the Bendigo zone is focused from the above the Mount William fault. So that's the boundary between the Bendigo and Melbourne zone. If we zoom in and look on a smaller scale, essentially what we see is we see gentle folding and then the folds tighten and then an actual planar cleavage forms. And then we see continued compression, the folds will lock up and actually fail, and we'll see low displacement faults cutting across those structures, and that's where an important site for gold mineralisation. So there's a series of low displacement shears that are linked by hydraulic extension fracture mesh, and that is open at times of fluid overpressure. And the fact that the Castlemaine group is a rather heterogeneous package of sandstones, siltstones and shales means that that fracture network is highly irregular and a little bit unpredictable. But it's during the shortening events that we see the best amount or the largest amount of focused fluid flow along those structures. In the top left-hand corner, what we've got here is there's kind of a Goldilocks zone where you need to be able to step in from those major intrazonal structures. You need to be a distance from them to actually see where there's a single phase of deformation and it's not been overcomplicated by polydeformed deformational processes associated with movement, progressive movement along those intrazonal faults. So that's pretty significant for the location of gold mineralisation. And if we look at these, we can back these observations up with empirical observations, and we see it's not always the case, but obviously in all these examples, Ballarat, Wattle Gully, Four Eagles, Fosterville and Lockington, we do see that relatively high-grade mineralisation in these systems is associated with relatively shallow portions of these structures where they're cross-cut anticlinal structures. Moving on to the fluid source, it's pretty easy to generate a lot of fluid, so prograde metamorphism will do that of both the Castlemaine group and the metabasalts. So we see a common PTT path in these origins of rapid burial and slower temperature increase, so there might be an offset in time from the compressional event to the generation of fluid. The most important temperature is 550 degrees, so that's right at the green schist amphibolite transition, and we see that transition is 100% controlled by temperature, nothing to do with pressure. The key thing that's produced is an aqueous carbonic low salinity fluid, and the key mineral reaction for that is the breakdown of chlorite to amphiboles. But also we couldn't explain the CO2 composition of the fluid solely on the basis of that reaction. So we're also at that transition, we're also breaking down carbonates as well to put CO2 into the fluid. So there's work done under the GSV's Gold Undercover program on the noble gas and halogen compositions of fluid inclusions related to gold mineralisation in Victoria. We see here, so it's a plot of argon 40 over 36 and just argon 36 content of the fluid inclusions. And generally what we see is that's in the right ballpark for being a metamorphic fluid. We do see variation in the actual content, and that's based of a function of the CO2 H2O ratios in the actual source rock, but also things like fluid rock interaction as well. One important observation is that on here, it's Fosterville that's got the biggest envelope, and maybe these processes or a combination of these processes are more evident at Fosterville than the other deposits, and that may explain higher grades or potentially higher endowment. Moving on to the halogens, so even though these are low salinity, the halogens are important because they're a conservative tracer of how the salinity was acquired. So we look at bromine-chlorine ratios and iodine-chlorine ratios, and we see there's a variation essentially from west to east. So we see Stool sits in the magmatic box, and that's likely because the salinity is partially acquired from the metabasalts, which are co-located with mineralisation at Stool, but not in the other systems. And then as we move into the Bendigo zone, we see higher iodine-chlorine ratios, and finally out into the Melbourne zone at deposits such as Woods Point and Walhalla, we see high iodine-chlorine ratios, which signify there's been interaction of the mineralising fluid with organic rich sediments. So sulphur and likely gold are sourced by the pyrite to pyrrhotite conversion, which is also at that effectively takes place at that transition from green schist to amphibolite facies metamorphism. And the likely sources for that have been the metabasalts and also the Castlemaine group. If we look at the sulphur isotopes down here on the left-hand side, don't worry about Fiddler's Reef. We're not sure about the paragenesis of those samples. But we see mostly in the range of +5 to -5. So that's either signifying that it's sulphur that was derived from a magmatic source, and that could be the metabasalts, or that we had sulphur from a variety of sources and it just became really well mixed. And that's not impossible given the large fluid flow paths that we're talking about in these systems. If we look at the actual content of the gold and arsenic content, which is obviously an important pathfinder in these systems. In the volcanics, we're talking 0.5 to 5 ppb gold, and arsenic 0.1 to 1 ppm, arsenic. And in the Castlemaine group, in the black shale units, and the black shale units only, not the sandstone or siltstone, we're talking an order of magnitude, greater than 10 ppb gold, and then an order of magnitude higher arsenic. And that's pretty significant because that just higher endowment in those elements may suggest that they are a more likely source of the metals, but wait. At Bendigo, there's been a pretty extensive pyrite laser ablation study done by the guys down at Codes that actually saw a pretty amazing depletion in gold and arsenic as we convert diagenetic pyrite to pyrrhotite. So we see that the mean gold content of the diagenetic pyrite was 0.6 ppm, and in the pyrrhotite, it's almost essentially, it's 0.04, so essentially there's been a crazy efficient geological process to extract that, and same with arsenic. And then as we go from hydrothermal pyrite gold contents and arsenic contents in the turbidites themselves, and then into laminated quartz veins, and then into the reefs, we see a gradual increase in those gold and arsenic numbers. So the theory here is they were actually tracking the metal movement through the system. But as Ross has said, so the black shale is a really good source, but in the Castlemaine group, it's regionally, we're talking less than 5% black shale. So even though it could be a really efficient process, we're thinking that there's a large thickness of metabasalt, which most likely represents a more voluminous source. And then if we compare it to stratigraphy in the east, in the Tabarabra zone, we have ore division sequences there that are almost exclusively black shale. So what's the difference for that? And in terms of exploration implications, is it just because the Tabarabra zone's been relatively underexplored? Is there differences in the metamorphic grade? That's not likely. So there's a few things to think about there. So we've got our gold source and we've got our sulphur source, and now we need to look at a transporting mechanism to transport it from the source into the sink, into the deposit. So gold's transported as Au1 plus in two sulphide complexes, and it's the low salinity fluid, and the electronegativity of gold means that gold will go with these sulphide complexes, but copper, zinc and lead will be left behind. So that's why we see not so much enrichment of those systems, of those elements, which would be transported by chloride complexes. And that also explains the similar geochemical behaviour of arsenic and antimony in these systems. And the diagram on the top left there is an FO2 pH diagram, which demonstrates that gold is most soluble under near neutral pH and below the sulfate buffer there. So if we look at the optimal conditions for the sulfur release to get the sulfur into a sulfide complex to transport the gold, we're also looking at that green schist amphibolite transition. And in the bottom left, what we see on the left-hand side is there's a yellow window there, which is essentially the sulfur-bearing window in peelites. So there's a large area relative on the right. So there's on the right, that's the sulfur generation window for mafic rocks. So even though we might be invoking the metabasalts as a good source of gold, sulfur may have been an important sulfur source was likely the metabasalt, the carbonaceous sediments. And all the thermodynamic modelling seems to point towards that sulfur can be 10 times the amount of sulfur can be generated from the mafic rocks, from the carbonaceous beta sediments. With the metabasalts, it's a little bit more difficult because any of the sulfur would be taken up by iron silicates. So what actually makes the gold precipitate? So there's a variety of reasons that we can investigate, and the big one that most people always go to is the rapid depressurization in areas of dilation, and that's great because we've obviously got a lot of areas of dilation, but what that rapid decrease in pressure generates is also a lot of physiochemical changes, which actually explain why the gold drops out of solution. So there's a variety of pH. FO2, as you saw on those previous diagrams, can drive gold precipitation and the activity of those sulfide species, plus also temperature. So below around 200 degrees, it becomes nearly impossible to transport gold as sulfide complexes, so it'll just drop out. We can do it through a series of reactions, so simple decreases in sulfide complex activity. We can do it through pyrite formation, and that would explain why some gold is locked in pyrite. And we can also do it through chem-absorption. So when you generate arsenopyrite in these systems, it slightly lowers the pH, which obviously is a pretty efficient way to drop out the gold from solution. And we can also look at the actual fluids. What can the fluids and the wall rocks tell us about what's going on? So there's the role of CO2. So we see a lot of evidence of phase separation in these systems, so a lot of variation in the liquid and vapour ratio, and a bit of variation in the CO contents in those phases. So what that does is when CO2 unmixes from the fluid, it drives to a lower pH, and you pop out gold that way as well. And we can also drop it out through a interaction of the fluid with a reductant to drive, to drive gold precipitation. There's also a lot of people who have spoken about the role of methane. So methane is important in some deposits. It's not immediately identifiable in a lot of the fluid inclusions in the Victorian systems. But what methane does is, again, it unmixes and lowers the FO2. So we're not talking about pH. It lowers the FO2 in that bit that gets unmixed and relatively increases the FO2, and you drop out sulfur that way. So gold that way. So that's why in systems such as WA you get a lot of magnetite. And what's great about some of these, we can actually see evidence for these in the rock, so that's pretty neat. So we look at there's muscovite alteration, so high aluminium muscovite alteration associated with the quartz sericite pyrite assemblage around the gold systems in Victoria. And we also see a lot of carbonate, that evidence for the CO2 unmixing in the veins and the wall rocks. And speaking about the preservation, again, it's coming back to those three unroofing events, which bring the orogenic gold systems in Victoria progressively through to close to the surface over time, but also since the Devonian has been relatively tectonically quiet. Obviously, there have been periods of erosion which have formed the alluvial goldfields that have historically been worked. Just touching on dispersion, so this is just a cartoon schematic of lithogeochemical rock data, just demonstrating that the arsenic is a lot more mobile in the near surface environment than antimony and gold, but obviously those can be used as potential vectors to mineralisation. So just summing up, we've got multiple reasons why gold's enriched in the Bendigo zone in these world-class orogenic systems. We've got three major orogenic events, so the Benambaran, the Bindian and the Tabarabaran, that occur over 65 million years. We've got two plausible metal and sulphur sources, and that's great because two is always better than one. And we've only got one fluid. And that pathway architecture, so we've got numerous faults and mesh networks to pump fluid from the source into the gold systems, and they're all in a suitable orientation to be reactivated by these three shortening events. We've examined why. We've got numerous precipitation mechanisms that explain the variable gold deportment that we see in the Bendigo zone gold systems, and the geological characteristics and alteration assemblages that we see in the rocks. And that near surface preservation due to those three unroofing events and relative tectonic stability since the Devonian. And that's it.